Thanks, John. Can you hear me well?
Yeah.
All right, great. So it's really hard to talk about pulse EPR in 45 minutes or so. So my goal today is not to educate you how to do pulse EPR, but rather sort of instruct what is the terminology, what people are talking about when they describe EPR experiments. And we go from there. We'll have a, EPR2 practical, where we'll be talking more into details what goes into measuring pulse EPR. And we'll introduce pulse techniques a little bit more detail there. So here, mainly we'll be talking about principles. Is that too loud? It is a little bit. All right, let me put it down a bit. So there's only one book that I can really recommend at this point, the Blue Bible. It's the Principles of Pulse EPR by Paramagnetic Resonance. You cannot see here, but it's by Arthur Schweiger and Gunnar Jeschke. It's a really good summary of what pulse EPR is about. Some of the techniques there never will be applied for bioinorganic systems, but just keep that in mind. All right, so this is exactly what we will be talking about. Technically, our unpaired electron senses all interactions around. Some are larger, some are smaller. And if you are lucky and the EPR line width is small enough, you can resolve them no problem. And you've seen beautiful examples of that in the previous talk. Unfortunately, in many cases, the line width that we are getting is just way too large to tell anything about the system. So what do we do? Of course, we can give up. But that's not an option in my book. So the other option is to use more advanced technique called pulsed EPR. This one allows, through magic trickery of pulsing microwaves through the system, significantly improve our spectroscopic resolution. Now, the immediate goal is we can detect weaker magnetic interactions. The other goal sometimes is that just get more precise information out. There are cases when continuous wave EPR is just bloody complicated. And to resolve those, you need to do a little bit more using pulse EPR. So that's what it's all about. And just to nail this information home, this is really distorted. Weird. All right, but anyway, so this is sort of a spectroscopic picture of a molecule. We'll have our paramagnetic center, let's say molecule, metal. In this case, on the background, you see a hemoglobin, I believe, or myoglobin, actually. Then you would have immediate ligands that may be magnetic, and you'll have interaction between them. And if you are lucky, you will be observing them in continuous wave EPR. But in many cases, we are interested to see a little bit more. We want to learn more about the electronic structure of the system. We want to learn about the structure of the system. And there we have to look at much weaker interaction with distant nuclei. Another option that is available to pulse EPR is to look at distant interaction with another spin center. When two spin centers are close to each other, you can use continuous wave EPR to tease out the interactions, but generally pulse EPR is a much better choice there. So this is why. Now, before we go further, I want to sort of lay ground and just drive home the message that conceptually pulse EPR and continuous wave EPR are pretty different. Continuous wave is an absorption spectroscopy. We blast our sample with microwave, it absorbs it, that's all we detect, that's the effect. In pulse EPR, we're pulsing microwaves, one after another, then we wait a little bit and see if sample screams back at us. So that screaming is in the form of transit emitting microwaves. So this is an emission spectroscopy. One advantage of that is that detection and excitation happen at separate times. So there's less tricks we need to do to improve our signal-to-noise resolution. Continuous wave EPR is a direct method. You always get an EPR spectrum out of it. That's all you have. You can do more tricks, temperature dependence, power dependence, all these kind of things. But in the end of the day, what you have is an EPR spectrum. And you can see it as it goes on your screen. In pulse EPR, situation may be very different. In some cases, yes, you get the spectrum right away. But in many cases, you need significant post-processing of your data before you can understand what they're seeing in the screen there. And one other point that I really want to point out is that pulse EPR is quite sensitive to a variety of relaxation effects. And what it can result in is that you can see beautiful, noiseless, continuous wave EPR spectrum, yet you will see zero signal in pulse EPR. This happens. You have to watch out for that, especially for high-spin systems, or systems that contain a lot of metals in it. All right, there's that. And just a final point on that, technique-wise, continuous wave EPR spectrometers are a lot less expensive. So basically all you have is microwave source, high-quality resonator, and then pretty much detection. That's all you have. Of course, there are trickeries, how Art was explaining. There's a lot going to that, but nonetheless, technique is relatively simple. With pulse EPR, we need to produce pulses, and we need to produce them very precisely with a nanosecond resolution. That drives the price up pretty quickly. And you have all of these components that we'll be talking about in the practical. All right, so I'm not going to talk about any techniques in particular, but sort of just to throw some acronyms at you. Here's the categorization of all techniques together into essentially three classes. Electron peak echo envelope modulation experiments, such as 2, 3, 4 pulses seams, there are more. High score, my favorite flavor, hyperfine sublevel correlation spectroscopy. All of these are time domain experiments where we tease out information about the interaction of electron with the nucleus from the perturbation of the time evolution of the spectrum. So this is time domain spectroscopy. Double resonances, this is a whole class of techniques that basically imply we need more than one pulse of different frequency in the same pulse sequence in order to get something out. You probably heard of electron-nuclear double resonance. This is another technique that teases out electron-nuclear interactions. You have Eldor-Tech NMR, which is a little bit of an exotic technique at the point that also does pretty similar effects. And then electron-electron double resonance technique is somewhat different because this one is used to detect interactions between two unpaired electrons. It's a time domain spectrum, but you still need two different frequencies in order to do the stuff. And then I will completely omit talking about relaxation studies. That's why I say it's broadly defined, because I think in that case, if I start talking about it, we will not have lunch today. All right, so yeah, basically I'm not going into details of any EPR experiments. I rather would like to focus on what we can actually get out of those experiments. So the basic principle is following. We can turn our paramagnet into a transient source of microwave radiation. If we turn it out of equilibrium, then time evolution of this out of equilibrium system will be perturbed by the presence of other magnetic spins around, nuclear spins and other electronic spins. And by observing the outcome of this electron spin evolution, we can access information about, sorry for that, information about spin-spin interactions. All right, so in order to understand what we're actually doing, we actually have to look into what spins are doing during our pulse experiments in a timely fashion. So here's a little bit of animation for you. Okay, in external magnetic field, each individual spin will be processing around the axis of the external magnetic field, which is z-axis in this case, with a frequency that is Larmor frequency. Okay, and if you put all the spins in the sample together into one point, they will form sort of a cone that will be all rotating like this. And if you sum all of these spins together, you get a sum magnetization that will be stationary and pointing along the external magnetic field. Fine, this is all beautiful. And of course, Larmor frequency will depend on the G value and also the magnetic strength. So stronger the magnetic field, faster the spins will be processing. Don't worry, they don't get dizzy. All right, so that's simple. Now, in EPR experiment, things are a little bit more tricky. Of course, you have this external magnetic field. Now I put it in the axis that points towards us. This is the resonator, and as you already seen, the resonator there to separate electrical and field components so that our sample only senses magnetic component of the microwave radiation. What Art didn't tell you, that this thing is not static. The magnetic field constantly oscillates back and forth with the frequency of magnetic radiation, electromagnetic radiation. So, and direction of those vectors is always orthogonal to the external magnetic field, which is why we call it perpendicular EPR. All right, now, how this all looks in our vector model there. Things are like this. Let's forget about this for now. Let's talk about the complicated stuff. So here is the oscillating magnetic field due to the microwave, which we call B1, by the way. Here's our cone of spins. And if you can see, there is this green arrow that represents magnetization. And what happens is, as long as we have this microwave applied, the spins will be constantly oscillating. Now that's kind of complicated. So we can make it a little simpler by turning it into a rotating frame. We can, if we can go along the Larmor precession with our camera and constantly follow that. And in that case, we emit the precessions around the z-axis. And that makes it a little bit simpler. And then the picture will look like this. So we have a static magnetic field from the microwave, and our magnetization will be processing in the plane orthogonal to that field. To make it a little bit more simple, it looks like this. All right? This is our static frame. Everything just moving around jolly well. And in the rotating frame, we'll go along and just see what happens inside the carousel. Does it make sense? All right. So basically, if you sum this all together, the result of the microwave pulse is turning our magnetization out of equilibrium in the x-z plane. The longer we have our microwave pulse, further the turning will go, and we'll keep going over and over and over again. So here are a couple definitions. We call it pi-half pulse if we wait with our microwave long enough for the magnetic moment to turn into the x-axis. So 90 degrees. If we wait twice longer, we'll get 180 degrees motion. And that's what we call pi pulse. Again, precession happens with the speed, with the angular speed that's related to the magnitude of the external magnetic field, or in this case, microwave field. So higher microwave power means higher B1, which means precession will happen faster. And this is a game we play a lot in pulse EPR. We can adjust the power to change the length of our pi half and pi pulses. And that will become more apparent why we need this a little bit later. So, just a couple of definitions. First of all, we call polarized state a state of the system where all the spins are in the same spin state. So we have m sub s equals -1/2 and +1/2. I'm sorry, this resolution is a little weird. But anyway, so this is one polarized state, and we can transfer to another. So another polarized state. The way we do this, we flip things 180 degrees. So to transfer polarization, we have to apply a pi pulse. Coherence is a state. Now, people that actually know this stuff, they will throw bananas at me, because this is nowhere near to be a correct description. But so that you understand what we are talking about, here it is. So coherence is a state in which spins oscillate between two states. So spins are technically in a limbo between two states, and they constantly go around. And the way math works is that the sum magnetization of this process will be that magnetization is in the xy plane. Okay, we can create coherence from polarization by applying a pi-half pulse. We can transfer coherence back to polarization by applying another pi-half pulse. And this is essentially the terminology we're dealing with. A couple more. Transition moment is the probability of changing the state. As simple as that. Now, a very important one. We were talking about doing something to our sample and then it shouts back at us. Well, in this picture, it means that the magnetization is in the XY plane. So we have an EPR signal coming out of this deal if magnetization is somewhere either on X or Y axis or somewhere in between them. And then we can have some kind of definition. We say if it's along X, it's real. When it's along Y, it's imaginary. That's an actual language Brooker uses, which I find a little weird, but nonetheless. Another term that's a bit more accurate is in phase and out of phase. Remember, we're talking about rotation frame, and we're focusing on the rotation with the lumbar precession, right? So what if we are not like this? What if we are like this, and we're turning? So that will be in phase, this will be out of phase, all right? Okay, now, another very important concept that is non-existent in continuous wave EPR, and that is pulse bandwidth. So in continuous wave, we're constantly blasting with microwave power. That means we have a very good idea what the frequency is of the radiation. When we have pulses, that's not actually the case. We're not exciting one particular frequency, we're exciting a range of frequencies. And shorter the pulse, broader the excitation profile will be. The result of that is that we are not just exciting one particular frequency, we're exciting spins of different frequencies here. For instance, if we have an EPR spectrum, and each point in the spectrum is defined by systems that have different G values, all right? And we would basically go through magnetic field. We have resonance here, we have resonance here, or resonance here. And that's what comprises these three G values, for example. Well, in pulse EPR, because we are exciting some sort of a range of frequencies at the same time, we'll be exciting all of these three transitions together. What that means, again, in rotating frame, we are fixed to one particular frequency. And this is the one we call stationary. And the precession along this frequency we call stationary. Everything that's below or above that frequency will still look precessing. We can call it the cold spins, the ones that precess with slightly smaller frequency, and the hot spins, the ones that precess with a faster frequency. Now, what that means is, if we talk about pi-half pulse, we create a coherence. Now, because we have this range of frequencies, there will be those that are right on the x-axis, and there will be those that will be moving away from the x-axis. There will be cold spins and hot spins, and then as time progresses, this goes around. And if you sum all the magnetization, total magnetization of all of these situations, you'll get less and less and less magnetization out of the system. And again, we detect by looking at the total magnetization along X or Y, okay? So this is sort of an animation of that. If you look at the total magnetization, it will be dropping down as time progresses after the pulse. And this is what we call free induction decay. All right, we can make it a little bit more complicated. What if after a pi pulse we apply a pi-half pulse, we apply a pi pulse? So we start with an FID, free induction decay, and then pi pulse will be turning things 180 degrees. All this pancake will just flip upside down. What happens then, because hot spins and cold spins are still moving with the same frequency, that didn't change. But the cold spins will become in front of the pack, and hot spins will be behind the pack, and they will be all catching up together. And then, of course, they will fall apart. So we'll see a transient signal goes like this. And that will be something we call electron spin echo. Speaking about romantic, echo. All right. So, but basically, that's the whole principles of pulse EPR. We're taking our system out of equilibrium, we perturb it, and then we observe what happens here. And I can tell you that one of the methods is when you utilizes directly this pulse sequence called Nico experiment. And if we change the length delay between the two pulses, nuclear spins will perturb things a little bit differently, so you'll see a modulation in the electron spin echo. But this is as far as I want to go with this, all right? Because there's something more important to talk about, and that's what we're actually getting out of those experiments. Okay, so back to this picture. Notice something common there. Mostly we'll be talking about interaction of unpaired electron with the nucleus. And turns out in pulse EPR, what we're essentially doing is a EPR detected paramagnetic NMR spectra. So essentially we are doing NMR here. Therefore, what I will be talking about is NMR. So what we care about with the spin Hamiltonian here is three components that associate with nucleus. We have nuclear-Zeeman interaction, obviously. Something to think about. Just think about why in continuous wave EPR you do not see nuclear Larmor frequency. Okay, just think about it, and you can tell me during the practicals. All right, and another interaction like this is nuclear quadrupole interaction. If you have nuclear spin that's more than 1/2, you will have this interaction to deal with as well. There's parameterization to that. You have the magnitude and the rhombicity of the quadrupole. I'm not going into detail of this. I think it's suffice to say that this is an important parameter that reports on the chemical nature of the nuclei we are detecting. So this could be very useful to identify nuclei that you're looking at. As far as the nuclear-Zeeman interaction goes, this is where we're deviating from NMR. We don't care about isomer shift. So we just have a tabulated frequencies for our Larmor frequency here, and just call it a day. Simply because the isomer shift interactions are much weaker than what we can detect. They're pretty much covered in the line width of our Endor, ECM, or other techniques. Now, this is what we're after most of the times, hyperfine interaction. And again, this is something you can already see in CW EPR in most cases. But when we're looking at more the weaker interactions, we have to do pulse EPR. But nonetheless, this is all the same. I have to put apparent hyperfine interactions here with an asterisk, just sort of a warning for you that if you have a system that has more than one unpaired electron that are sort of interacting with each other, think of fluorine sulfur cluster, for example, then hyperfine interactions you will be observing, they will not directly correlate to spin density. You have to think of spin-spin interactions first, and then derive something called spin projection coefficients there. And then from there, extract the spin density populations. This is something I'm not going to talk much about, but here's a really good book, EPR of exchange coupled systems, that describes it in detail. It's Bencini. Again, the resolution is really weird. All right, so let's start with isotropic hyperfine. Just to briefly reintroduce it again with slightly different formula. It's a little bit more generic, but not by much. Two things I want to emphasize here. Again, spin density at the nucleus is encoded there. And then you have to worry about that the hyperfine coupling, and that's in general for all hyperfine coupling interactions, it will be scaled by the nuclear G value. If we go back, you can see, for example, protons and deuterons. And they have Larmor frequencies that are about 6.5 times different. So all your hyperfine interactions will be scaled down if you replace protons with deuterons. And this is a really cool game to play sometimes. All right, but then you can actually figure out the degree of spin density at the nucleus that is tabulated numbers for having 100% spin density on the s orbital on the nucleus. And if you do a cryo reduction, this is just one of the spectra I pulled out from my files. You can clearly see these sharp lines that correspond to about 1400 megahertz, which is actually a hydrogen radical. All right, and I believe we have a cryo reduction practical as well, so you'll be learning about that more. Now, anisotropic hyperfine is most interesting one because that encodes all the structural information. Now, there are many different reasons why you have an anisotropic hyperfine. What I'm talking about to you here is extremely simple. Again, please do not throw bananas at me. It's an approximate description that only valid for cases when unpaired electron and nucleus can be treated as points in space. That's what is called point dipole approximation. And in that case, you can derive this kind of a formula where you have, again, a hyperfine coupling scaled by nuclear G value by 1 over r cubed, where r is the distance between electron and nucleus. And you have this orientation dependence. And commonly, people use parameter that just basically takes all of this that's in front of the orientation dependent term and call it T for dipole coupling. All right. So if you plot this coupling as a function of the angle between the dipole vector and the external magnetic field, you'll get this sort of dependence. Now, for educational purposes, it's good to think about spins as little magnets that always follow the external magnetic field. When you have external magnetic field along the dipole vector, then you have a situation where north looks at south, or other way around, for two magnets, and that's attraction. When you turn things 90 degrees, you have north to south to south, so that's a repulsion. So you have, by turning from 0 to 90 degrees, you turn interaction from being positive to negative, or other way around. Just something to think about. Again, absolutely not acceptable if you talk about quantum mechanics, but it's good to have in mind when you're trying to understand what this means. All right, so you have this coupling that goes from -1 to +2 if you scale it by t. And of course, there will be a point on which there is no hyperfine coupling at all. And this kind of interaction is axial, meaning you only care about this angle between external magnetic field and the dipole vector. So what happens on the other angle doesn't really matter. So that's why you have two principal components of hyperfine tensor called the same and called A perpendicular. And there will be one selected orientation. We call it AZ, and that's the one when magnetic field is along the dipole vector. Okay? When we put these all ideas together and try to understand what will be the NMR frequencies that we'll be observing here, this is the formula. You don't only have to worry about the hyperfine constant itself, you have to worry about this little term that we can think of as an anisotropy at a certain angle. It goes from 0 to some number to 0 again. It's sort of a slope of the frequencies here, of the frequency diagram here. So, and again, as you do an NMR measurement, you would see peaks that are spread by dipole coupling, then it will go to 0, and then again something spread by double dipole coupling. That's with the no isotropic coupling present. If you turn that on, things will shift around a bit. If it's a positive isotropic, they will shift one way. If you turn the other way, you'll shift it the other way, all right? So that case is basically just to illustrate where the frequencies will be. Now we have to think of what's actually happening in our sample. Well, we usually don't have a control over the orientation of the molecule. If you can do single crystal, you're the king of the world. But typically, that's not the case. Usually, you have a frozen solution where all orientations are occurring at the same time. So in that case, we need to think how to transfer all this into powder average spectrum. And it's like this. What you have to think is how many molecules are there where the dipole vector, is exactly oriented with external magnetic field. There wouldn't be many. But how many molecules will be out there that are oriented so that dipole vector is orthogonal to the external magnetic field? Well, quite a few more, because we don't care about the angle that is orthogonal to the magnetic field. And this is how people usually draw things like that. Imagine you have a sphere of all possible orientations of the molecule with respect to external magnetic field. And then you select on that sphere those molecules that contribute to a certain situation. For example, the ones that over here will show you a band on the sphere like that. For a situation where you have the 0 degree, there will be only a little dot on the top there. And the area pretty much tells you number of molecules in that particular case. So if you put it all together into powder averaging, you'll get a spectrum like that. So there will be, for a parallel case, you'll have pretty much no intensity at all. And for perpendicular, you'll have quite a bit more. Okay? So this is for positive isotropic coupling. And for negative, you can derive the same idea. It's just things will be upside down. All right. So that's really good. Now, we were talking about hyperfine coupling that's a lot weaker than nuclear alarm frequency. And this is essentially what we were trying to derive here. When there is no isotropic coupling, you'll have this kind of situation we call the Peak pattern. And then things are spreading out if you have isotropic part. When you have a strong coupling case, things are a little different. The peaks that you see on your NMR spectrum will be centered on the half hyperfine coupling and spread by double armor frequency. This is true for isotropic one. Anisotropic will be like this, or like this if you have some kind of isotropic part to that as well. So this is something to watch out when you do pulse EPR measurements. Now I can actually talk to you about this. This is why pulse EPR can become so powerful. Orientation selectivity. So we were talking about NMR spectrum and how it changes with orientation in case of anisotropic coupling. We have a G anisotropy still. And our EPR spectrum is defined by G anisotropy. And again, with the pulses that we are using, we will be exciting only some fraction of that spectrum, well, given that the spectrum is broad enough, all right? And in that case, in our particular pulse EPR experiment, we'll be either selecting only these few molecules or these molecules over there, or in case of rhombic case, situation with the orientation selectivity will be slightly different. Nonetheless, what we do with this, we just select only part of the EPR spectrum, which also means when we measure NMR, we only see a fraction of that dipole coupling, the dipole spectrum. And if you put this all together, it looks like this. So I just flipped the EPR spectrum sort of 90 degrees for convenience. And imagine we can do our NMR experiment with having, with selecting different fields from here all the way there. And then we record NMR spectra for that. What you'll see is this kind of patterns where things are just changing all the time. What's really interesting, what's really good about this is that the pattern that we'll be seeing in this field-dependent study will depend on the relative angle between the principal axis of the G tensor and the hyperfine tensor. Now we have an access to pretty much not only the distance by looking at the magnitude of the coupling, but also the orientation of the dipole tensor with respect to the G tensor. And so this is what you will get. And of course, at this point, there is no easy way to tell things. You actually have to simulate. All right, so that was NMR spectrum. Now, just coming back to this for a brief moment. So there are all these kind of techniques, and what did I want to say? Yes, let's just focus on something that gives us this NMR spectrum. ECM, high score, or ENDR, and we forget about DEER and relaxation studies for now. In the EPR2 folder, there is a poster that I uploaded. This is the poster we have hanging next to the EPR machine, and it's really cool cheat sheet that you can use for sort of remembering which sequence is what. So there are two different most commonly used pulse sequences for ENDR, MIMS and Davis. They have a different setup. Most importantly, for MIMS ENDR you need non-selective pulses, meaning you select pretty much all frequencies associated with the what did I want to say? Associated with the hyperfine splitting in the EPR. Davis center is different in the sense that you have to be very selective. What that means, in MEMS center we have to use very short microwave pulses, and in Davis center we have to use very long pulses. Our problem is, in any case, I don't know if you can see here, there is a periodic blind spots for MEMS center, and for Davis there is a blind spot in the middle. And that's the reason why Ender techniques are usually used for relatively isotropic hyperfine couplings. eSIM methods are very different in the sense that they're mainly used for anisotropic coupling. 3-pulse eSIM is a one-dimensional method, and the high score is essentially a two-dimensional version of that. A little bit more about the eSIM here, why we have, if you see here, although there are some perturbations due to the blind spots, technically you still have the NMR spectrum visible in Ender. In eSIM it's not the case because it relies on excitation of forbidden transitions. And that relates to this parameter B, which you already seen before. Modulation depth is defined by the B square with some constants there. So the shape that you'll cut out with the eSIM is slightly different. You'll have this kind of a bell curve where the ends of the NMR spectrum will not be visible at all, which is a problem. But nonetheless, it's something to watch out when you look at the spectrum like that. Okay, so in the last, 5-10 minutes, let me just go through a few examples that sort of highlight ability of pulse EPR to resolve structural and, well, mainly structural questions. So one of the really prominent one is by Hoffman and Broderick, where they looked at the binding of S-nosyl L-methionine into 4N sulfur cluster in the radical SAM enzymes. If you're not familiar, radical SAM enzymes is a class of enzymes that uses this molecule, reductively cleaves it, producing a very potent oxidizing agent called 5'-deoxyadenosyl radical. And that spreads through a wide range of different reactions afterwards. Back in the days, people didn't know that SAM was actually binding to the 4N sulfur cluster, and more than that, I think back in the days people were really thinking iron sulfur clusters are there only to transfer electrons. So this was one of the sort of breakthrough to this kind of idea. So what they did, they labeled different parts of the molecule with isotopes. There's 17O, there's carbon-13 on this side, and there is nitrogen. And all of this Ender spectra proved beyond doubt that there is this kind of staple motif that, of binding of the SAM to the iron sulfur cluster. What's also quite interesting is that they labeled this methyl group. And despite being sort of distant from the iron sulfur cluster, through the orientation selective Ender, they identified that the coupling is not entirely axial coupling. There is a little bit of isotropic component, and there was a little bit of rhombicity to that. And the conclusion was that there is a little bit of spin density on this moiety here. So there is actually electronic interaction between the iron sulfur cluster and this part of the molecule. And they used this information to derive the idea how reduction of the 4N sulfur cluster results in the cleavage of this bond here and the production of the 5'-DA radical. All right, second example is my own. So this is pretty old study where we looked at the iron anhydrogenase and used eSIM and high score to identify nitrogens in the vicinity of the active center. What we did here was we just used 3-pulse eSIM, one-dimensional method, and we just sweep it across the magnetic field. And you have this kind of complex pattern there. You can also see here. For instance, here you can see protons and the Larmor frequency changing because we're changing magnetic field. But from this complex pattern, we identified two different nitrogens. One was, and they have very different quadrupole coupling in them. One of them was identified as cyanide, this proximal cyanide, they call it. And the other one we couldn't actually identify, because back in the days, we weren't sure whether there was nitrogen in this ditylate bridge or not. Well, it turns out if you put it there and you calculate what quadrupole coupling you're supposed to get, it was pretty much spot on what we have observed in ECM and high score spectra. So this was pretty much the first experimental proof that there was a nitrogen in this ditylate bridge. And that was very important because this nitrogen is what accepts the electron after heterolytic splitting of hydrogen in this system. All right, then just to sort of highlight what we will be doing in the EPR2, this is the paper, the whole practical we were based on. This is an example where we try to see if vanadyl is a good structural mimic of a ferryl intermediate and mononuclear non-heme enzymes. And we used high score with orientation dependence to tease out the distance between the vanadium and the closest proton in the substrate taurin using deuterium labeled substrate. We didn't just get the distance, we also got the angle pretty precisely. Yes, and another thing I want to mention here is that this is one of the cases where EPR shape, which is pretty complex, is defined not by the G anisotropy, but the hyperfine anisotropy. More specifically, hyperfine of the vanadium. And the orientation selectivity that we used was actually due to anisotropy of the hyperfine coupling, not the G tensor. And I think we're almost done. Just to sort of point you into the direction of DEER studies, this is the work by Stefan Stoll and Lysine, which is actually pretty awesome. So what they did is they labeled strategically some parts of the proton with spin labels, and using double electron-electron resonance, they looked at the distance between spin labels. The reason they did that, because there was a notion that when the camphor enters the site, it changes the conformation of the protein. It's almost like a mouth. It's like, I want camphor, I want camphor. Then, I got camphor, I got camphor. So, and you can easily see this in DEER. You see that the distance between spin labels is a lot larger when there is no substrate present. And the whole protein tightens up when there is, when camphor enters the active site. And with that, I would like to finish and let you have your lunch. I hope you enjoyed it. And again, if you have any questions, I will be for some part of the EPR2 and also for some part of the EPR4, which is data analysis. And I already see Eckhart Bill here, so we are safe with with doing the EPR analysis session as well. All right, thank you.
So we have time for a few questions. We have 2 or 3 minutes. Nothing from the audience. Let me ask you this.
Sure.
It isn't clear. What causes the blind spots in DEER? In MIMS and Davies?
Well, there is no easy answer to that, because depending on the sequence, blind spots originate from different parts of the problem. So one of the problems with, let's start with the simple actually. In a Davis Endor, what you have to do is to have a selective microwave positon selects one of the 2 EPR transitions that are split by the hyperfine coupling. The problem is if the hyperfine coupling is very small, there is no way you can do selective excitation. And as you are not selective anymore, there is no Endor effect. And that's the blind spot for that. For MIMS Endor, things are a little bit more tricky. What you have, you create a graded polarization. As we have precession of spins, they will be affected by nuclear resonances. And this will evolve as well. And if you pose at different times, you either create nuclear polarization that you can affect by RF pulse, or you cannot. And this goes in a circle. So that's why you have this. For some couplings you will see an Endor effect, for some you don't, and goes back and forth. And that will depend on how long you wait between the pulses. So that's short answer.
Okay. We've absorbed a lot of information from these 2 lectures, and I'd like to emphasize that much of this information we're going to be doing in the practicals. So what This is just basically a taste of what's to come. We'll be going minutes from that, and you'll have some hands-on experience. And that's, I think, where the real learning takes place. So, have a good lunch.